partial derivatives, when using a function of more than one variable, we want to know how the value of the function varies as we change one variable while holding the others constant. Consider a function of two real variables, f colon all real numbers squared yields all real numbers. The slope of this function at a point is a little more complicated to define than the slope of a function with a single argument, because the slope of the function at a point now depends on direction. For example, let f of capital N and capital E equals capital N squared minus capital E squared plus 1. The variable names are chosen to evoke a map where capital N reflects the latitude and capital E denotes the longitude. The value of the function f evaluated at a point on this map can then be thought of as corresponding to the altitude height. Figure capital A dot 3 shows the surface and contour lines of this function. This function takes the value of 0 at the origin but changes in quite different ways as one moves away from the origin, depending on the direction of the move. If one were to move directly to the northeast, then capital N and capital E would increase at the same rate. Hence, their squares do too. Thus, if one moves directly to the northeast or southwest, the altitude does not change. In the figure, the curves in the open parentheses capital N comma capital E close parentheses plane are contour lines of the surface above the plane. The curves show that if capital E increases at the same rate as capital N, the elevation remains constant. However, if one begins at the origin and heads directly north, then capital N increases while capital E remains fixed. Once altitude increases in this direction. If, on the other hand, one heads directly east, capital E increases while capital N remains fixed. And one heads downhill, open parentheses, after traveling capital E units, one attains an altitude of 1 minus capital E squared, close parentheses. Going just north or just east gets at the idea behind the partial derivative. The idea is to vary the value of one variable while holding all the other variables fixed. This procedure also gives us an easy algorithm for computing the partial derivative of f with respect to, say, capital N. Just pretend that capital E is a constant and compute the ordinary derivative. Thus, we have the partial derivative of f with respect to capital N. The partial derivative of f of capital N and capital E with respect to capital N equals the partial derivative of open parentheses capital N squared minus capital E squared with respect to capital N equals the partial derivative of capital N squared with respect to n, capital N, equals to capital N. And the partial derivative of f with respect to capital E, partial derivative of f of capital N and capital E with respect to capital E equals the partial derivative, open parentheses, of capital N squared minus capital E squared with respect to capital E equals the negative partial derivative of capital E squared with respect to capital E equals negative 2 capital E. In the special case in which f is a function of only a single variable, the partial derivative is exactly the same as the ordinary derivative. Partial derivative of f of x with respect to x equals the derivative of f of x with respect to x. In the general case in which the function f colon all real numbers to the power m yields all real numbers depends on several variables, one can think of the partial derivative of f with respect to, say, the first variable as measuring the direct effect of a change in the first variable on the value of the function, while neglecting the effects that a change in this variable might have on other variables that might influence the value of f of x. Just as the ordinary derivative of an ordinary derivative is called a second ordinary derivative, there are also higher order partial derivatives. For example, the partial derivative of g of x sub 1 and x sub 2 with respect to x sub 1 is written as the partial derivative of g of x sub 1 and x sub 2 with respect to x sub 1. The second partial derivative of g of x sub 1 and x sub 2 with respect to x sub 1 is written as the second partial derivative of g of x sub 1 and x sub 2 with respect to x squared, while the second partial derivative of g of x sub 1 and x sub 2 with respect to x sub 2 is written as the second partial derivative of g of x sub 1 and x sub 2 with respect to x squared sub 2. We can derive second order or higher order derivatives that involve the repeated differentiation of the function with respect to more than one variable. For example, if we differentiate the partial derivative of our function g of x sub 1 and x sub 2 with respect to x sub 1, the partial derivative of g of x sub 1 and x sub 2 with respect to x sub 1, with respect to x sub 2, we obtain the cross partial derivative, the second partial derivative of g of x sub 1 and x sub 2 with respect to x sub 1 and the partial derivative of x sub 2. The order of differentiation doesn't matter for the functions as we usually study. According to Young's theorem, the second partial derivative of f over the partial derivative of x sub 1 times the partial derivative of x sub 2 equals the second partial derivative of f over the partial derivative of x sub 2 times the partial derivative of x sub 1. If the cross partial derivatives, the second partial derivative of f over open parentheses partial derivative of x with multiplied by the partial derivative of x sub 2 and close parentheses and the second partial derivative of f over open parentheses the partial derivative of x sub 2 times the partial derivative of x sub 1 exists and are continuous. Similarly, the fifth partial derivative of g of x sub 1 and x sub 2 over the partial derivative of x squared, or the second partial derivative of x sub 1 multiplied by the third partial derivative of x sub 2 indicates partial differentiation of g with respect to x sub 1 twice and with respect to x sub 2 thrice, thus yielding a fifth order partial derivative. Figure capital A.3, illustration of partial derivatives. The figure shows the surface and contour lines of the function f of capital N and capital E equals capital N squared minus capital E squared plus 1. If we move only in the capital N direction, the elevation rises at an increasing rate, whereas if we only move in the capital E direction, the elevation falls at the same increasing rate. The curves in the capital N and capital E plane are contour lines of the surface above the plane. The curve shows that if capital E increases at the same rate as capital N, the elevation remains constant.